The dot product of A and B, so A is A1, A2, B is B1, B2, is defined as A1, B1, which is the multiplication of the two x coordinates, that's A1, B1, plus the multiplication of the two B coordinates, or the multiplication of the two y coordinates, sorry. So vectors A and B are orthogonal if your dot product is 0. So I want to find the dot product and determine if they're orthogonal for, hold on, I gotta change my pen color, for U and V. So my U dot V is 5 times negative 3 plus 1 times 15. This gives me negative 15. 1 times 15 is 15. I get 0. And since my dot product came out as 0, they are orthogonal, meaning those two vectors, if I were to graph them, are perpendicular to each other and at a 90-degree angle. 2, find the dot product and determine if they're orthogonal. Again, this is just another one. So U dot V is 4 times 8 plus 5 times negative 6. All I'm doing is adding or multiplying the two x's together right here plus the multiplication of the two y's together. That gives me 32 plus negative 30 gives me negative 2. Oh, sorry, gives me positive 2. That's my dot product. So they're not orthogonal. They're not perpendicular to each other. Okay, if I want to find the angle between two vectors, I guess I forgot to put the formula in here. That's cosine theta equals your dot product divided by the magnitude of each one. So if I want to find the angle between those two vectors, I'm going to do cosine of theta equals, that's negative 3 times 7 plus negative 5 times 12 over, and remember, this does not mean absolute value when we're dealing with vectors. It means magnitude. Sometimes you'll see two lines written there. Negative 3 squared plus negative 5 squared times square root of negative 7 squared plus 12 squared. Oops, it's not negative 7 squared, it's positive 7 squared. I don't know why I said negative. Let's go back and fix that. Okay, so my suggestion when you put it in the calculator is do second cosine, because you need to do inverses to solve for theta. And then type that whole fraction that's up here. And remember, if you need to get the fraction bar on there, that's alpha y equals. And you can get your fraction bar on your screen. Alpha y equals enter. And when you do that, you should get that your theta is 179.29 degrees. A lot of this is just plug and chug into the calculator. Okay? If I set up another one, the only difference between this and the last one is here I'm giving you linear combination form instead of component form. So all I'm going to do is just write them in component form. And then we're going to do the same thing. So basically I'm going to do cosine negative 1. And then you're doing your dot product, 13 times 6 plus negative 5 times 2 over the magnitude of each. And again, it doesn't matter when you're doing the magnitude if you put the negative 5 or not. Make sure if you put if it's a negative 5 or a positive 5, because you're going to square it anyway. But make sure that if you do put the negative on there, that you put a parentheses around it. Otherwise, it's not going to do it the same. And through the magic of me putting it in the calculator, you're going to get 39.47 degrees between the two vectors. Okay, vector projection. Let U and V be non-zero vectors such that U equals W1, W2, where W1 and W2 are orthogonal, and W1 is parallel to or a scalar multiple of V. So in other words, if you come down to my picture down here, I've got two vectors. I've got vector V and vector U. If I want to do the projection of U onto V, that means I basically want to drop down a perpendicular from U to V, which means that vector that was once this length from my initial point to my terminal point has now been squeezed down in order to make this a 90-degree angle. Remember, if two things are orthogonal, they have to be at a 90-degree angle. So that's why we're dropping this down perpendicular You can use this for a lot of force problems. If you're shining a flashlight on a wall, if you're shining a movie on a wall, you're projecting something from one surface onto another. So we're just basically dropping down a perpendicular. This is what we call W1, and that vector that you drop down, that is W2. So to find this vector projection, you're going to do this formula here that will take that vector, and this dot product over your magnitude squared will shorten it. Okay, so keep this formula in mind on the next screen when we do. Find the projection of u onto v, then write u as the sum of orthogonal vectors, one of which is the projection of u onto v. So first thing I need to do is I need to find my W1, which is my projection of u onto v. So that you do by doing u dot v over your magnitude of v squared times v. So that ends up being your -3 times your -4 plus your -2 times your -1 over your square root of -4 squared plus -1 squared squared, and all of that times vector v. So you're taking a vector, and this whole formula right here is what will shrink it down. Remember, it's kind of like when you found a unit vector and you divide it by its magnitude. It's going to do something like that, where it's going to do a process to shrink it down. And when you stick all of that in the calculator, you'll get 14 over 17 for all of this. Because remember, your square and your square root would cancel out, so that's why there's no decimals down here. You shouldn't have any decimals. -4, -1. So if you multiply those together, you get -56 over 17, -14 over 17. We're going to have to add another screen. Okay, second step from the last problem is if I want to write the sum of two orthogonal vectors, remember you had a W1 and a W2, and that gave you your U vector. So U equals W1 plus W2, that's just resultant vector. So if I want to find this W2, I have to do the U that I already know minus that W1, which was your projection of U onto V. My U was -3, -2. My W1 that we found, or my projection, is -56 over 17, -14 over 17, which gives me 5 over 17, -20 over 17, if you do your math. And so when it wants you to write U as a sum of orthogonal vectors, you're going to write U, and then W1 was the -56 over 17, -14 over 17, plus that W2 that we just found. And if you were to add these both together, add these two, W1 plus W2, you would see that if you add them together, you're going to get your U of -3 and -2. Okay, for work, there's 4 ways that you can look at it. Work equals the force of your magnitude times your distance, which is your conceptual version. Work can be your force times your PQ vector. That vector part's really supposed to be over PQ. It kind of got messed up in the translation, which is the dot product of force and the distance vector. You can look at work as a projection of F onto PQ. This is the long way to do it. Or the one that we're going to use the most is cosine theta. So that takes into account the angle. Times your force times your magnitude vector, the vector that you're moving at the most. So if I have a toy wagon, don't make fun of my wagon, that is pulled with a force of 25 pounds, it makes an angle of 20 degrees, and I want to move it 50 feet. So my work done is just cosine of my angle times my force times the distance you want to move it, and that's going to give me 1174.62 foot-pounds of force. Foot-pounds of force. Okay, Her last one is slide at a carnival has an incline of 60 degrees. A 50-pound girl gets not part of the way down, part of the way down. Sorry, that was a bad typo. Ignoring the force of friction, what force is required to keep her from sliding down any further? So if I have a picture and I have a little girl sitting here, this is my vector V. She's weighing 50 pounds, so that is my force due to gravity. So my force is negative 50. That's your force due to gravity. And since she's going down, that vector is 0, negative 50. So if I drop a perpendicular from that force vector onto here, I'm trying to basically find this vector right here, this W1, that it's going to take her not to slide down. So to find the force required to keep her from sliding down, you're going to project the F, this is my force vector, onto V. And so the vector V, remember, is a 60-degree angle. So that vector is represented by cosine 60 degrees, sine 60 degrees. So that is 1/2 square root of 3 over 2. So that's what the V vector is. So if I want to find my W1, I have to do my projection of F onto V. So that's F with the dot product of F and V over my magnitude of V squared times my V vector. I have to figure out how to shorten that vector. Okay, and I'm probably going to have to do this on the next screen because I'm going to run out of space. So again, I'm doing projection of F onto V. So that's going to give me 0 times 1/2 plus negative 50 times square root of 3 over 2, because you're doing the dot product of the force vector, and, oops, I forgot times V. So then that's 1/2 squared times, or divided by the magnitude squared times your V vector. So when you square this and square root it, that goes away. So you end up with negative 50, oops. Let me start that over. So you end up, when you do this whole entire thing, you end up with negative 43.3 square root of 3 over 2. So this really is the vector, but this is how much force is going to take her from sliding down. And since if we go back to the diagram, since the force is going down the hill, that's what the negative is for. The negative is just the direction. So it's going to take 43.3 pounds of force to keep her from sliding. Sliding down the hill.